In the previous video, we were introduced to refraction and dispersion. Over the course of the next two videos, we will derive some important consequences of these concepts. Here we have a prism. This prism demonstrates what happens when a beam of light encounters another medium. At the interface of the two media, some part will be reflected, while the other part is transmitted into the new medium under a refracted angle. But how much of the beam will be reflected? How do we determine in which direction the beam will propagate in the new medium? And what determines the degree of dispersion? Answering the last two questions is the main objective of this video. We will learn what material properties affect the angle of refraction and how to calculate this angle. Furthermore, we will find that sometimes light isn't transmitted at all into a new medium, but entirely reflected. Finally, we will learn what determines the level of dispersion. As to the question of the direction of the refracted beam, the answer was provided by the Dutch astronomer Willebrord Snellius. He stated that the angle of transmission depends on the angle of incidence and refractive indices of both materials. The law that describes this relation is known as Snell's law. Snell's law states that the ratio of the sines of the angles of incidence and transmission is equal to the ratio of the refractive indices of the media. It can be gathered from Snell's law that if n1 is greater than n2, the angle of transmittance will be smaller than the angle of incidence. Furthermore, we can see that by increasing the difference between the refractive indices, the angle at which the light beam is refracted will also increase. The angle of reflection, however, simply equals the angle of incidence regardless of the refractive indices of the two media. There is an important implication of Snell's law that we will derive by putting Snell's law into practice. Let's follow a number of beams emitted from the blue point source. The first beam arrives at the interface on the normal incidence. If we apply the provided refractive indices and an angle of incidence of 0 degrees, we find that the beam is transmitted on the normal incidence as well. Next, we consider a second beam with an angle of incidence of 20 degrees. With a refractive index of 1.5 and 1, the beam is refracted at an angle of 30.9 degrees. A fraction of the intensity of the beam is reflected. A beam with an angle of incidence of 35 degrees is refracted at an angle of 59.4 degrees. This shows that as the angle of incidence increases, the angle of refraction increases even more strongly. When the light beam is incident on an angle of 41.8 degrees, Snell's law shows that the beam will propagate perpendicular to the plane of the incidence. This angle of incidence, for these particular refractive indices, is known as the critical angle. When a light beam is incident under an angle greater than the critical angle, the beam will no longer be transmitted. Rather, the beam will be entirely reflected at the interface of the two media. Total reflection only occurs when moving to a material with a lower refractive index. Total reflection takes place if the sines of the angle of transmission is greater than 1. Let's consider, for example, a beam incident on an angle of 60 degrees, which is well past the critical angle of 41.8 degrees. The sinus of the transmission angle equals 1.3. Since 1.3 is greater than 1, the light beam will be totally reflected. The angle of reflection equals the angle of incidence. We just saw that the critical angle occurs when the angle of transmission equals 90 degrees. Since the sinus of 90 degrees equals 1, the critical angle can be calculated by the inverse sine of the ratio of the outgoing media to the current media. We can use this figure to explain an occurrence of total reflection that is used by photographers. We can see that from the blue point source, the range of angles from which light is transmitted into the second medium is limited. Now we reverse the direction of the light beams and assume the white and blue areas to be air and water. Then what we would see from the perspective of the dot is known as Snell's window. The critical angle from water to air is about 97 degrees. Therefore, when a picture is taken underwater, facing the sky, we can see the outside world compressed into a cone of about 97 degrees. Outside of this cone, the bottom of the sea is reflected. However, since most of the light is absorbed in the water, the area outside the cone usually appears dark. Total reflection also has an important implication in solar cells. The Lambert-Beer law dictates that a certain amount of energy of a light beam moving through a medium will be absorbed. This amount depends on the absorption coefficient of the respective medium and the traveled distance. This figure illustrates an incident light beam denoted by the red circle, entering a silicon slab. The light travels through the silicon at the refracted angle theta until it reaches the backside of the slab. At this silicon-air interface, a large fraction of the light intensity is transmitted from the slab, while the rest of the energy is reflected back into the slab. The reflected fraction passes through the cell once more. At each subsequent silicon-air interface, a fraction of the energy is transmitted from the silicon slab. After a few passes through the cell, hardly any of the initial light intensity remains. Let's now consider the same light beam entering the silicon slab, but now we assume that, for some magical reason, light enters at an angle of refraction greater than the critical angle. Light enters the silicon, gets refracted, but now at the second interface all of the light intensity is reflected back into the silicon slab. Each time light encounters the silicon-air interface, all of the energy is reflected and none of the energy is transmitted. The light beam exhibits total internal reflection and undergoes many passes through the silicon slab. Consequently, the path length of the light beam through the silicon is much larger. Total internal reflection can therefore be used to greatly enhance the absorption path length of light in the absorber layer. We previously derived this equation for the critical angle of total internal reflection. Since the critical angle depends on the refractive indices of the media, it can be influenced by varying the materials encompassing the absorber layer. In the case of silicon and air, which we just observed, total internal reflection already occurs for incident angles greater than 13.4 degrees from the normal. Glass has a larger refractive index than air. The refractive index mismatch between silicon and glass is therefore smaller. As a result, the critical angle is larger and is equal to 20.4 degrees from the normal. This demonstrates that a larger refractive index mismatch leads to a smaller critical angle. A small critical angle is preferable since it allows a larger fraction of angles to be internally reflected. So far, for convenience sake, we have ignored the fact that the refractive index of a material is wavelength dependent. The critical angles on the previous slide, for example, have been calculated at a wavelength of 500 nanometers. The critical angle will be different at a wavelength of, for instance, 900 nanometers. We should therefore formulate Snell's law a bit more rigorously. This graph shows the refractive index of several silicon alloys as a function of the wavelength. The visible spectrum ranges from violet light with a wavelength of around 400 nanometers to red light around 700 nanometers. We can see that the refractive index of the silicon alloy 1 only shows a small wavelength dependence in the visible region. The refractive index of the green silicon alloy 3, on the other hand, is strongly wavelength dependent. This means that light entering silicon alloy 3 will show a relatively high level of dispersion. The level of dispersion is therefore very much a material-dependent property. The greater the wavelength dependency of the refractive index difference between the two media, the greater the dispersion will be when light propagates from one medium to the other. Now in summary, Snell's law describes how light is refracted and reflected depending on the refractive indices of the media involved and the angle of incidence. We saw that if the angle of incidence is greater than a certain critical angle, total reflection will occur. This only occurs when light moves towards a material with a lower refractive index. We derived this critical angle of total internal reflection for different material interfaces. And we saw that total internal reflection can strongly increase the absorption path length of a photon in a solar cell. Finally, we looked at the wavelength dependence of the refractive index of a number of silicon alloys. In the next video we will discuss the Fresnel equations, which describe how much of the light intensity is reflected and transmitted at each interface.